Good morning and welcome. I'm Brian Bailey, Technical Editor for Semiconductor Engineering. I'm here today with Praveen Tiwari, Senior R&D Manager for the Verification Group in Synopsys. In the past, formal verification has often been seen as a problem which explodes very quickly, leading people to believe that it's only suitable for small designs or small parts of a design. What are some of the ways that we can actually use methods that reduce the problem or the size of the problem and allow us to get good results from formal verification? So in the past, one of the reservations about formal verification is that the problem quickly explodes, leading people to the assumption that it is only applicable to small parts of a design. Can you explain why this is not the case and some of the ways in which the problem size can be reduced?
Sure. So I think the way to approach the state explosion problem, which still remains, it's a technological limitation, but the way to solve it is using the 3 steps process. I think for any verification flow, the planning stage as to what is being verified, how is it going to be verified. Secondly, the verification process itself. Along the way, how do you measure, let's say, the complexity, the proof depth that you have, is it good enough, and finally sign off. So all the 3 need to be taken into account when we are talking about state explosion or the problems of the complexity of formal verification. I think one of the first things that one can do to elevate this problem during the planning stage itself is to choose blocks which are really suited towards formal. Some of the things like estimating the complexity of the problem beforehand, even before the first line of assertion is coded up, in terms of what is the design complexity, how many FIFOs, counters, and things which really are bad for formal. Those characteristics of the design can be evaluated upfront to estimate what is the verification time cycle that would be spent in formally verifying the design.
Is that something which you just get from experience, or are there ways that you can judge the complexity?
So I think there are 2 orthogonal points to answer your question. One is, each design can consist of certain behaviors which are very good for verifying with formal. For example, the control paths. Now there are certain characteristics of the design like data path verification which might not be very suitable for formal. So attacking the ones which are kind of the sweet spot for formal, and for those areas of the design, estimating based on the available design statistics. For example, one can take the cone of influence from an output of a design to figure out how many FIFOs and counters are there. What are the depths of those FIFOs? Are they really huge FIFOs? Are they synchronous, asynchronous? These are characteristics that can be easily extracted from the design. And then certain base rules can be applied to arrive at a complexity estimate that can aid in the planning process.
Okay, so we've done our planning. You gave an example a couple of times of using a FIFO. Are there things that we can do in formal to reduce the sizes of the FIFO or the complexity in other ways that in effect bring the size of the design down and yet still serve as a useful basis for doing the formal proof?
Absolutely. So there are a couple of approaches that can be taken. If the design has been kind of designed for formal, by that I really mean that the design is parameterized, it has all the real good parameterization schemes available. So one can reduce the size of the FIFO, yet not lose the functional intent of the design. Now in many of the cases that might not be applicable. So in those cases, one can actually replace the FIFO with a more formal friendly abstract model. That would go a long way in terms of aiding the formal proof itself.
Okay, now one aspect of formal that I think confuses a lot of people who are not familiar with this form of verification is the notion of a bounded proof. Can you explain what a bounded proof is and the limitations of that information in terms of formal coverage?
Sure. So there are only 3 types of results mostly that one can expect from a formal tool. If there is a failure from the starting state, which is normally the reset state, you get a counterexample and a waveform to debug. On the other hand, you can get a full proof, which effectively means from all the illegal states of the system, there is no path from the reset state to those illegal states. So that's the full proof for you. In case of bounded proof, the tool is actually trying to go from the reset state in time forward as far as it can get before, let's say, it is stopped by the state explosion. So at a lower level, what it means is that for n cycles, if the bounded proof depth is n, from reset, all the states from the reset to those n cycles are proved to be clean for the corresponding property. It, however, doesn't mean that the design is absolutely clean, because the tool has not been able to explore all the possible states. Now, you had a question about what does it mean with respect to coverage. In fact, bounded proof is also very good, in the sense that there could be some value extracted out of a bounded proof. If, let's say, there is a property which is proven up to a bound of n, and if we can realistically prove via some other mechanism that all the influencing design nodes in the cone of influence of that property can at least be reached in that bound n, you have a very good statistic in terms of mostly this property is actually clean. So that's how we can actually tie up the cone of influence code coverage with the bounded coverage for a given property.
Now, you mentioned that the proof is from a reset state. Could I perhaps constrain the problem in other ways, such as starting from particular states or controlling certain inputs?
Yes, absolutely. So, in those cases, now there is a common technique normally used for cases which are too huge for formal. It's a commonly known as a bug hunting technique, where one can mix, let's say, simulation and formal in a more interactive fashion, where the starting states are kind of derived out of certain points in simulation. Thereby, the users can still get some value, but I would like to point that this technique can never give you full proofs. It's a good bug hunting technique, but would not normally, solve the whole problem in terms of getting a complete formal proof for the particular property.
So tell me a little bit more about, bug hunting. When would you start using that, and how would you use it?
Okay, so for designs, for example, I'll take an example, let's say post-silicon debug. Now, there is a bug which has been found in terms of the top-level simulation or emulation environments. And one needs to zero it down to a block which is potentially the problematic one. Now, one option is to create a complete formal test bench for the given block and verify it end to end, but let's say because of the time constraints that's not possible. So what one can do is take the simulation vector which showed the problem from the top level environment, load it up in the design at the block level, and write the corresponding assertion, the property that you are interested in, and let the tool choose the points from the same simulation vector to explore around that area, to zero in on the bug and the potential fix. So post-silicon debug is one very common example where bug hunting is actually very useful.
Okay, thank you very much, Praveen.
It's a pleasure, Brian. Thank you.